So my name is Kurt, and I work at Alibaba, and currently I'm a Chief Flink PMC member, and this is today's agenda. For those of you might or might not know that Flink 1.9 added a pluggable planner architecture, and we introduced a new Blink planner. I'll give you some background and some motivation why we add this planner. And also we have some short introductions about some major features and the improvements we did in Blink Planner. Before I start, I want to just emphasize this is a joint efforts with entire Apache Flink community. As you will see, it's kind of changed the whole project's architecture, and we did a lot of changement, and there's no single person or single team can do this. So thanks for the whole community. So a little background. This is Flink original architecture. Flink can deploy it in various environments like a single JVM process as well as cluster and the cloud. Flink has a unified distributed streaming data flow. We call it runtime, and based on that, we have two dedicated APIs, one for streaming and one for batch. And the table API and the SQL is actually built on top of them. And the original planner will translate the program, translate the SQL into these two APIs. So let me take a step closer to see the underlying of these two APIs. It's actually, you will find some interesting things in here that actually Ayosha have had a very good explanation about this in another talk called the Flink 2.0 architecture. He explained why there are two APIs for both streaming and batch, and what's the different requirements for these two processing modes, and as well as maybe some shortcomings. In short words, that we have too much duplications for these implementation details. We have to, every time we want to, because I'm mostly working in SQL, most time I want to add some features, we have to modify the whole stack. And I have to do it twice, one for batch and one for streaming. And there's no code can be used. We have different API, different translation paths, and also different codes, and actually also different execution modes. We have push-based operator for streaming, but we have pull-based driver for batch. So after some research and some POCs, we start to figure out that this is what we want, or the only thing we need is actually the streaming side. We can unify the whole architecture into this part. So this is going to be maybe the future stack looks like one more unified one. Like we have unified API. Below of that, we have unified planner who can do both batch and streaming. And we will translate the program into a unified DAG representation, which consists of stream transformation and the operator. But we still have to do it step by step without breaking any backward compatibility. So we still have let user have the choice to upgrade from older version to the latest version without breaking things. So we still need to support the old codes. So actually the community comes up with a very nice solution. We introduce a pluggable planner architecture, and we can keep all the logics into the Flink planner. And we can try everything new actually in another big planner, so we call it Blink planner. So this is actually some history of Blink planner, why we introduce it, and how does it look like in the architecture. So here's some features and improvements I have collected from Blink planner, but not all of them. If you might also find something interesting or useful after you try it out. I have split this into three parts. The one is common, used for both batch and streaming, and some streaming-specific features and improvements, and as well as batches. So let's start from the common ones. As you may know that we rework the whole type system in 1.9. And because we met a lot of limitations when we use the type information before, because it's come from runtime and it's different with SQL. So we think about to introduce a more SQL compliant type system for it. And after introduce it, actually Blink Planner is starting to use it with, so we don't use type information anymore. So we introduce some features like decimal. We can finally bring the precision and the scale information along with the type. And also we can bring the nullability information along with the type. And we also do some extending to type system type. But this is just the beginning. We still have a lot of feature to add in the future version, of course. So after we introduce a type system, we begin to seek some improvements for our common data structures. The most widely used data structure in SQL is actually a row. Look at this example. If we have a row consists of 3 fields, one is integer followed by 2 strings, it's actually backed up by a very simple JVM, Java's object array. Because we have to pay some cost to some lot of object headers or something other things, such a simple row would easily cost more than 100 bytes for your JVM memory. So it's space efficiency, and it will affect the CPU efficiency. So CPU cache line will be not friendly. And furthermore, if we want to access some fields from it, we have to pay the cost of boxing and unboxing. And most importantly, we actually faced a lot of serialization and deserialization problems, especially when you want to randomly access some field. You may wonder why the object array have to pay the price. It's actually we typically we will store the row in binary formats in byte array. Like if the data comes through network, transferring through network, it should be a byte array. And if we store the row in the state, it also have to be the byte array. So in this case, imagine that if the row has 200 fields, and you want to access the 100 field and do some sorting on it, you have to deserialize 99 useless rows fields before you can access the real field you want. So we start to thinking about it. If given that the fact that the row is typically mostly encoded, stored in binary format in byte array, why don't we just make a row? Its data is actually the byte array. So we introduce this binary row. It's the biggest advantage of binary row is there is no need to deserialize. Because we integrate it deeply with Flink's memory management, which will have a memory segment for each unit. And once you have some memory segment and you know the start offset of the row, and everything is done. And you have already can access the row. And more importantly, this binary row actually have the ability to do random access. Still the previous example, we will have some fixed length for each field. So each field will occupy 8 bytes for this fixed length part. Even it's like a string, it's a variable length row. So like a string, it's like an integer double, we can store the data as it is in this slot. But for some variable lengths, we will store the point, which points the actual address, which is store the real data in this case. So it's a really efficient and compact layout. We don't have to pay the price for deserialization anymore. And after introducing binary row, we realized that some complex field will also meet the same problem of row. Take string, for example. If you want to access the 100 characters of the string, you also have to deserialize the whole string into Java JDK string, and then you can access the character. So we also introduce a binary string as well as binary array and the binary map. We cover all the SQL's popular data structures, so everything works in binary now. So it's improved the efficiency, performance a lot. So this is actually we use this as a common data structure for Blink Planner. Let's talk about some data Skew data handling. Skew data handling is a very common situation. Will happen not only in classical batch processing, but as well as in streaming processing. It might happen in join or aggregation or other scenarios. Let's take aggregation, for example. In this case, we want to group by color and do some simple sum. And for each key, we will key by the color to the downstream operator. And for the same key, downstream operator will execute it in a single thread fashion. So it's very easy to be the bottleneck if some colors have a lot more amount of data than other colors. So it's very simple to do to improve it. We introduced some local combiner, just a map-reduce local combiner. In this case, we introduce a local aggregate operator after the map operator before shuffling, so we can partially aggregate the data in upstream operators. So this can redistribute the computation logics evenly, so the downstream operator will not be the bottleneck anymore. But sometimes local aggregation will not do the trick, especially when distinct aggregation involves. In streaming, we actually support we will use state to store all the detailed information about the distinct aggregates. In this case, we want to calculate the distinct IDs. We will store all the IDs in state, and we begin to shuffle all the state IDs to downstream operator. The local operator is useless in this case. So we have to introduce some other optimize for such case. Like we will have we will have a rule to do the optimization. The effect is very similar with we did the query writing. We will break the query into two parts. In the inner part, because the ID itself will be the bottleneck, so we split the IDs into multiple buckets, and we do the actual count distinct inside the query and sum it up in the out query. So this also can ease the aggregation skill problem. So combined with the local aggregation as well as this query writing, we have, I would not say we solve all the skill problem we see in aggregation, but most of them, I guess. Speaking of streaming, we also add some features and improvements only for streaming specific. The first one is, let's take an aggregation example again. For this aggregation, if we look inside the aggregate operator, you will see that for each record that comes in, we will first look up a state to get our partial result back, like the partial sum from state, and do the aggregation. Then we'll output some result. And also, maybe you should also output a retraction message first, and then with the correct message. And then we have to write it back into state with a partial result. So typically, each record would cost one state read and one state write, and also deserialization and the serialization. And it will generate one or two outputs. So what can be improved? The solution, the approach we took is also very simple. Instead of doing the calculation for each record, we will actually buffer the records into some heap memory. to hold the bundle. We will also have some triggers on the bundle, like we have some time limit for the real calculation to happen, or we have some size limit to this bundle. You can also use these two limits together. So the real calculation happens after the bundle triggers. So before we access state, we will actually do the in-memory aggregation before we access state. So in this case, we can reduce the access time from number of elements from the number of distinct key we have, right? Typically, it will improve performance if you don't meet the situation that your key is actually distinct with, you have all the distinct keys. In that case, it will be useless. But if you are running an aggregation query, actually, most cases you are supposed to aggregate with this key, aggregate some data with this key. So in real situations, we observed like 2 times to 10 times speed throughput improvement for like such a, like I think it's fairly simple improvement. Yeah, let's talk about dimension join. Dimension join is yet another very popular requirement. We receive such requirements frequently. It's also a very popular concept in data warehouse and also in streaming area. The most frequently asked use case is the user will have some fact table, unbounded fact table stored in some message queue like Kafka, and they have some static table, static data. They want to enrich the fact data with the static data. So sometimes it will store in files or in some database or in some key-value stores like HBase. So in this case, the dimension table itself might also changing itself, but most of the time the user don't care about it. So they only want to let the fact data join the dimension table join the latest dimension table. It's actually a quite interesting use case. It's not it's of course not a purely batch join, right? Because we have to deal with some unbounded fact table. It's also not the regular streaming join, because the regular streaming join, if something changed with in the dimension side, you have to trigger the calculation again. You have to recheck the wrong results you have fired and output some new real correct results. So it's actually different with both things. So the hardest problem question for this is actually, how did we write the SQL right? How do we write the SQL meet this concept and can reflect these requirements perfectly? It's not easy with the classic SQL, because the classic SQL, they only deal with static data. It's like a static relation. So with some help with some newly published paper, which Fabian is one of the authors, it's called One SQL to Rule Them All. There's a newly introduced concept, we call it a TVR, time varying relations. It's like a model of the tables, so treat it like it will change over time. And every time it changes, we have some version or timestamp on it. And also SQL standard have some temporal tables, it's kind of like implementation of this concept. So introduce some new keyword called for system time. Like it exposes the ability that whenever you want to access a temporal table, you have to specify the version, which version you want to access. So combine these two together, we have such a SQL. Let me explain a little bit. In this case, we have some orders stream, and for each order, we want to enrich the data with some product info. And the product table itself might change, and every time we want to join with the latest product table. So in this case, after the framework see the for system time, we will know this actually is a temporal table, and we have to do it with a temporal table way. And the version for this table is actually proc time. This is actually some tricky thing that we want to make the version equals to the order when we deal with the order data. In a short word, it's actually the same semantic with described in previous slides. It's actually each order data comes in, we want to join the product with the latest version. So this actually it's a correct cycle to write in this scenario. It's quite interesting. So for implementation, we have a lot of choices to do. We can either scan the whole dimension table in if it has some bin log or something. We can scan it into state, and after every order comes, we can look up into state. Or we can have some other choices, like we don't have to scan all the dimension table into Flink, but instead of it, we can look up for it. Because some like a database, some key value store, they have the ability to be lookuped. So we introduce some interface called lookupable table source. Like in this case, we will do lookup for the dimension table join. It's actually very efficient. Here is another quite interesting streaming use cases. You might know that it's impractical for streaming to do a global sort, except if you are sorting on the event time field. But if you want to sorting on an arbitrary field, it's quite expensive. So it's possible, but very, very expensive. Like in Flink's computation mode, we will keep firing retraction message and after following with correct messages. If you do a global sort, every time the order changes, you have to retract all the previous orders. Like if you have 1 million records and suddenly the orders change, all the orders changes, you have to retract the 1 million records, and then you output another 1 million record. It's very expensive. But if the user only cares about the top n elements, the story have been changed a little bit. Like if we, for example, in our case, if the user want to get the top 3 sellers for each category. So for such use case, first we can write the SQL in this way. I can maybe I explain a little bit. We will borrow the over window for this case. In over window, we will partition by the category and order by the sales. And also we will generate the row number for each record. And we will also select other information through this select star. And in the outer query, we will actually limit the row number into some, like if you want top 3, you can have the filter less or equal to 3. So after the Flink seeing this query, but for the inside query, it's actually the same situation. I mentioned that it's a global sort with an arbitrary field. What can we do about it? So it's crucial for us to find the pattern that this over window is actually followed by some filter condition. In our some optimization rules, we will consider this pattern and turn this over window with arbitrary sorting into a dedicated rank operator. This can avoid that the Flink will do a very expensive over aggregation. So the rank operator is dedicated. It is responsible to calculate the top n elements, and we also have other opportunities to improve this operator, like if whether this operator have to deal with retraction message, also whether the partition key is part of the primary key. In this case, we can improve the state structure. We don't have to use map state anymore. We can use some state with a more efficient state. Also, whether the order by field is monotonic. It also can help us to improve the data structure and the operator logics around it. The interesting about top 3 is, or top n operator is, if we extend it a little bit, we can actually do another interesting things in streaming. We call it a streaming de-duplication. It's just like a top 1, right? But in streaming de-duplication, we typically will have 2 use cases. Most cases we have 2 use cases. The first one is, imagine in duplication you have some sort of key, right? And the upstream, maybe due to some reasons, recovery or something, the upstream will generate exactly the same duplicate the records. So in this case, only the first message with the same key matters to you. So if you don't want to see all the other messages with the same key, this is one use case. Another one is actually your upstreaming is keeps refining the results with the key, like it keeps updating the results with the key. So in this case, it's like only the last row matters to you. All previous result message you see is useless now after you see a new result, new record. So it's quite interesting. We can write the SQL in this way. It's very similar with top n, and we call it top 1. And the only two things need to modify is first you have to limit the number to 1, and another trick is you have to order by the field to proc time. This is another. It will acting like the row will it's ordered by the time the framework see the row. So for such SQL, we can achieve the semantic of whether you want the first row the framework see or the last row if framework sees. So much about streaming. Let's talk about some batch improvements. For batch, is the biggest differences with batch is why batch can improve performance in some scenarios is actually bring by the data finiteness. Because if the data is finite, we can do a lot of more efficient algorithms like sorting, because it's very common for batch to sort something, and we have a lot of efficient sort algorithms, and so we first we introduce a push-based sorter. Like I said, we unify the whole architecture to a streaming fashion. So we have to make all the operator is doing push the fashion. Is means that all the elements will be pushed to operator by framework. So we change the core logic is very similar with Flink's original one, and we change the computation mode from pull-based to push-based. And we use some binary formats which introduced before, and we did some code generation to make the hotspot run more efficient. Based on sort, we also introduced a sort merge join and as well as sort aggregation. So a lot of sort-based algorithms is only available in batch. Also, we have some hash-based algorithms. Hash-based algorithms is more strictly than sort. It cannot be applied anywhere because it's not easy to apply the hash aggregate if the aggregate has a variable length partial results. So if the requirements meet, actually most of the time the hash algorithm will be efficient than sort algorithms. So we introduced the hash aggregate. Also with some with the binary formats we introduced, and we will have some improvements like auto detecting whether it's a hash mode, because in some cases you only want to select a distinct ID from some table. It's like doing a hash set. Also, we will find if the memory runs out, we will we will fall back to sort aggregation, and we can actually sort the hash aggregated data in the place without copying it out. In the place, we can sort it, and we can do a sort aggregate update. It's very efficient. As well as, besides with hash aggregator, we introduce a hybrid hash join, which is also very similar with Flink, the original one. We also changed it from pull-based to push-based fashion. And we did some extensions to make it support all kinds of joins. We support inner, left, right, and full join, as well as semi and anti-joins. Semi and anti-join is extremely useful if some subquery involves. So we also make some more functionality coverage. Like I said, we have more data types support, and we support all types of joins, and we did some subquery decorrelation, make the queries executed in semi-join or anti-join, and we did a lot of over-window enhancements. So adding these all things together, we've already achieved we can fully support TPCH queries in 1.9. Some wrap it up, and some thoughts about the future. Actually, Flink already took a big step towards the unified architecture. It's not a concept or a slogan anymore. Like we keep saying that streaming batch is a special case of streaming. This is actually really happens architecture-wise and code-wise. We are unifying this architecture. We also have a SQL's planner actually using this unified architecture, and can do both batch and streaming, process batch, both batch and streaming. And a little about the future, like maybe 1.10 or future versions. First, I would say we will definitely finalize our new type system. We have a good start, but we don't finish it all, so we will definitely want to finalize it. And we also want to finalize Blink merge things. And after that, we can have a full support of TPCDS queries. And hopefully after 1.9 release, we can receive some feedbacks about Blink Planner, how you use it, and is there something wrong, goes wrong, or something you are not satisfied with it. We hope, hopefully, some feedbacks can help us to improve. I won't list a lot of features here because this is actually all the ongoing features. Other features, like it's decided by community, not me. Yeah. Thank you very much. I would like to answer some questions.
Thank you, Kurt. Yes, there's a question there.
Great talk, thank you. I wanted to ask, the improvements you made, for example, bundling the updates on the state and so on and so forth, are also included in the normal engine, or are only when you are planning on SQL?
You mean which improvement?
For example, the bundle. I mean, it seems orthogonal to SQL.
Okay.
It's something that any Flink operator should do when aggregating.
It's right now it's only applicable in SQL. The reason we can do such optimization, I think it's easier to in SQL because SQL has some concept we can rely on, that we always doing some aggregation, right? We are not doing arbitrary aggregate. Like if take for example, if we want to borrow these improvements into the like a data string window operator, right? It's the things will got some more complicated because right now the user can write arbitrary window function on this data. So in this case, you can easily break the protocol. You are not following the rules we set it like SQL. So but I think we can borrow some ideas, but I don't think it will just work if we change this to data string also. Yes.
Any other question? Yeah.
I can ask another one. Yeah, now I forgot it. Yeah. How do you think to share? I mean, the pattern recognition thing on the SQL. I mean, it seems like it could be reusable by many projects that are SQL based, like how you recognize patterns inside of the SQL query by lexing the query. I don't know. Is that like pluggable outside of Flink? Or
You
it's,
mean share the planners?
yeah, also the pattern recognition in the query. Like you understand that if you have where num_row is equal to 1, then you have a top one query. I mean, it could be useful also outside of Flink.
I think so, yes. The reason for it is actually, as you might know, that Flink actually use calcite to do the SQL optimizations. A lot of things I have talked with is actually a rule or calcite optimization rules. It can be if the system is using calcite to do optimizations. There's actually a lot of systems doing this way. So if it can just copy the rules into their system and do a little modifications to meet their requirement. I think it can work. Yes.
Yeah, I see. Perfect.
Any other question from the audience? Okay, so thanks very much, everyone. Let's give a thank you to Kurt for the presentation, and the next one starts in about 10 to 15 minutes. So yeah, see you in the next sessions. Thanks, everyone.
Thanks.